Okay. Welcome to this year's OCaml workshop. We have an exciting program ahead of us. But first, let me bore you a little bit with a few opening words. We are very happy to have received that many good and cool submissions. So thanks to anyone that submitted. We try to get in talks within a diverse range of topics. And I'm sure there are ways in which it could be even better, but we are quite satisfied with the result. When I say we, more specifically, Sonia, Heinz, and myself were responsible for organizing the workshop this year. I'm here now. Sonia couldn't be here in person because right now she's 8 months pregnant. But she's attending from online, and so hi, Sonia. And we organize everything together. Maybe it's even more accurate to say that she organized a lot and that I help. Right, and I should also thank all the members of the PC who actually did all the reviewing for the submissions. So that was great. And finally, thanks to the OCaml Foundation that provided funding, a little bit of funding for registration fees for speakers that needed it. Maybe one day we can dream that this would be free, but alas, that's what we have right now. And so thanks also to the sponsor for the foundation that give it money to do that kind of cool stuff. All right, let's get to the cool OCaml stuff. And for that, Samuel has been waiting. I'll now give the mic to Stefan to introduce Samuel, and we can get started.
Great, thank you, and everybody welcome to the first session of the workshop on compiler features and optimizations. Our first talk will be Samuel Vivien talking about the design and implementation of modular explicits.
So hi, so I'm going to present you the design and implementation of modular explicit. So this is a new feature that PR was created to the compiler a few months ago, and it's currently going under review. Hopefully we'll have it inside the upstream compiler in the next year. So it's joint work with Didier, Rémy, but also the implementation was done with the help of Léo, Guillaume, Pierre, Nathanael, and Vincent from the Flamta team at OCaml Pro and Léo at Jane Street. So a bit of history. In OCaml, since 3.12, we have a feature called first-class modules that enables us to store a module inside a value, or first-class value, such as the sum all m above. And we can also unpack those first-class modules inside to have, once again, a module which enables us to use it as a regular module to take out fields inside this module. An example of the use case of this feature is to have dynamic modules inside our code, such as having a module that is defined depending on a flag. So depending on the value of a flag, you take module M1 or M2, which can be useful in some cases. So just say, oh, depending on how big I'm going to run my code on, I will use one implementation or the other of a certain library. A general use case of module is that first-class module is doing a let module to unpack the module locally, and this creates a scope. This happens a lot when you're having a function that take a module, first-class module as argument, and you might not be used to the syntax, but rather the one with syntactic sugar, where you unpack directly the first-class module as argument. However, there is some limitation with the syntax. So first example, I have a small signature add, which defines type T and addition on this type. And I want to write the function double that takes an X as argument, a module of a signature add, and use this module to do the addition between X and X. And we have a small error message when trying to type this code saying that X is of type alpha and was expected of type m.t. So this is a bit strange, but the second line says us that, oh, it was a problem with scope. And the thing is, when someone sees this code, you might want to write it, but you have no way of writing the type of this code currently in the OCaml compiler. And this is why the code is rejected. You cannot write the type, so it cannot be typed. A workaround will be to remove a dependency between the type of X and the module by defining a new type, type A, and saying that the type defined inside the module M is type A, and also that the type of X is also A. In this case, you remove a dependency, and you're able to type this function. However, what happens when I want to do it with a parameterized type, such as list? I'm trying to do the same thing with, I'm defining the type with a parameterized type, but the syntax doesn't allow this. And when I'm trying to restrain the signature of set to a parameterized type, it's also not allowed. So I cannot do this, so I'm stuck. However, we can just do a first-class functor to do this. So you write a functor, store it in first-class module, and you can do this once again. However, this is hardly readable and also extremely painful to write. A small example, if I have a signature S, which defines a type T, which is parameterized, and a function singleton that take a value and create a set of this type. So I want to write a function f that takes an element, a module x, and returns the singleton built from EL. However, so normally there was scholars saying this were in red, but this cannot be written. And if you want to write this code, you need to do this big code that is a bit difficult to understand. And if you manage to understand this just by seeing it, I'll be impressed. So to solve this problem, we just introduce a new type, which is module-dependent function. So this is not the same arrow as the one we have currently in OCaml, because it's a dependent arrow. However, it's the same syntax, which the big thing with this module-dependent function is that x can occur inside tau. And with this, we can express all the types of the function that were presented before and that could not be typed. However, we have a few restrictions with this new type in order to be able to do things with it. First thing is that a parameter can be depended on only if it's a direct unpacking of a module. For example, if we unpack a module inside a pair, it cannot be dependent on this module. If we don't unpack the module, we cannot be dependent on the module, with just the last case where it's directly unpacking the module, where we can have a module-dependent function. And also, when doing an application, we need to directly pack the module at the application. So in a way, we're just directly giving a module and taking the module directly back in order to be able to do things. And if we stay too long as a first-class module, we're just stuck. So small example of use case, I have a module type show, which is the same thing as the type class show in Haskell. So we have a type T and the show function that converts our type T to a string. And I have two modules, that is show int and show list, that define show for the corresponding types. And I can just write a small function show that take a model x and a value of the corresponding type defined in x and just convert it to a string. And I'm now able to write the type of this function. And from this, I'm able to print a list of integers just by giving the good module to the show function. So in a way, this is a way to emulate type classes in OCaml, just with writing the application by hand. So you want to understand how this works. So we are going to do a bit of typing. So when we have a module-dependent function, we give it an argument that is of a good type. We just take the return type of the function, and we replace all occurrences of a bound variable by the module. However, this does not respect typing in OCaml currently, because in a module path and a type, we can just have a module name and projection of a path to a certain field. We cannot just write an arbitrary signature or an arbitrary module inside a type. So to be able to do this, we need to be able to extract the module M to a path, and this path can be written inside types. But this is quite a huge restriction, meaning that when doing an application of a module-dependent function, you cannot just write a struct. However, just by doing a small eta expansion, we create a temporary path that can be used. And the OCaml compiler is able to do this through typing by just imagining that there is an X doing this and inlining replacing all occurrences of a bound variable by this x, and then eliminating the x from the scope and replacing it with all type dependencies that use this x by the definition of a corresponding type. And in a case of generative module, when you create a new type that is locally defined, then you have a scope escape. So we don't have any problem with soundness. And lastly, all this feature is also working with so the thing that we want in OCaml to be able to have principal types, which means that we, in some cases, want to be able to type without caring about the ordering of typing, and this feature also handle the principal mode because we want to have this kind of soundness in some cases, such as when typing standard library. So if I go back to my example, some of you might have noticed that the syntax that I used to define the show function is the same one as the one we currently use with first-class module. So you might want to ask, but this might cause a problem because we're already able to type some example of code with another type. And if we have two different types, this might pose a problem. However, we define both types to be compatible. In the cases where x doesn't appear in the return type, we have a module-dependent function that is not exactly dependable. So in these cases, we define both to be equivalent, and typing just go from one to the other, depending on which one is more expressive for the use case we're going to do. And also, unification does a few things that might be considered black magic, such as when doing unification, we merge both types together in order to propagate information. However, when unifying two module-dependent functions, we look at them up to alpha equivalence, meaning that we might be able to switch between x1 and x2, which might pose problem when looking at tau1 and tau2. In order to solve this problem, we unify both names together, meaning that after unifying those two module-dependent functions, we only keep one name out of both. So if you have an example using Modular Explicit in the future, and you see that your function doesn't have the same bond name that the one you use at the beginning, it's just that during unification, we've merged it with another name that was written somewhere else in your code, and we need to choose one out of both. So this might seem a bit strange in types that are shown or in error messages, but it's perfectly normal. But as we are doing unifications on name, we can do capture with it. So meaning that when unifying both names, if x1 was already appearing in tau2, we're just binding the variable somewhere else, and this might be a bit problematic. So we've added a small check to ensure that we're not doing any capturing. This is something that already exists with polymorphic values inside objects or records. It might be a bit problematic in some edge cases with recursive types. And in this case, we might lose a bit of expressivity. However, this problem already exists with polymorphic values. And I didn't manage until now to generate an example that was limited by this restriction. So most likely, you will never see the difference, that there's this small restriction hiding somewhere in the code. And hopefully, in the future, it will be removed. So yeah, we have a cool feature that enables us to use module a bit more easily. However, there is still work that's need to be done in order to let people use module freely in OCaml inside the core language. And I hope that all this feature will one day be in the compiler. First thing will be parametric signature. So as you might have seen in the example before, when doing the restriction of a signature to a certain type, we have quite a lengthy syntax, just as when I want to restrict the signature egg to a type a.t, I need to write egg with type t equals a.t, which is quite long. And when you have lots of signatures that are going to be restricted, we might want to have a more shorter syntax to be able to write it, and a.t egg could be a way to do this. It's the same thing as parameterized type, but with a signature. Another feature that will be in the same direction will be to be able to give directly types as argument to functors. So there's some libraries nowadays that give types in a functor, but you always need to wrap it inside a module. An example of this is OCaml graph, that sometimes have functors that don't do any restriction of the type they need. And so this is quite lengthy to be always say, oh, I'm defining a module that contains one field that is a type, and could be useful to just give a type directly. And by using value restriction, we can just also give a different semantic to this kind of functors compared to regular functors that take a module as argument. And last feature that could be useful in the future will be modular implicit. So for those of you that haven't heard about this feature, it was initially proposed by Leo Watt, Frederick Boer, and Rémy 10 years ago in a paper called Modular Explicits. And so the idea is, if I take my example with show from before, I can just define modules that I label as implicit. And afterward, when defining the show function, I can just say that the module as argument will be an implicit argument with a syntax that looks a bit like implicit argument in rock. And then when doing application, I can just omit the argument because we know which module will be given based on the signature that is already restrictive and the fact that we know that the argument is a list of integers, so we only have one module that can be given as argument. However, in some cases, you might have another module that you might want to give, not be restricted with, like with type classes in Haskell, of the fact that you have a type class, so you cannot define a new one for the same type. In those cases, you can just give it by hand and give another module by hand that is not the default one. It's an implicit argument. You can use the default one or give your own. So as a conclusion, modular implicit is a new feature that does not increase expressiveness, but greatly increase conciseness. And also this feature escaped the original goal that was just being a step towards modular implicit, and now it's a cool feature that just can be used as a feature itself. However, it's still just a step toward making OCaml a bit more user-friendly in some cases. And also, just as a reference from a talk from last year from Leo, we can have parametric values, polymorphic values easily with first-class module, with modular explicit, such as in this case, we can define a type T that take module as argument that just define a type, and then we have a polymorphic values. And this is a way to do polymorphic values that are given as argument to a function without having to go through objects or records or whatever you might want to do in order to have a polymorphic values that is not instantiated when given as a parameter of a function. And if you want to have a more in-depth read about this topic, there is the PR on the OCaml compiler. You can also test this branch of the compiler by using the small opam command that are listed above. And if you want to read even more about this topic, there's a long paper that we've written with a few other people that talks about typing and soundness of this feature. And thank you. Do you have any questions?
We've time for some questions.
Thanks for the talk and for the work in implementing this. So you started off saying that we don't have a syntax for sort of introducing a locally abstract parameterized type. Mm-hmm. Would it be possible to add that syntax? I mean, I think this is useful for other things, but, but in terms of sort of motivation, it just seemed, I mean, when you presented that, I was just wondering, you know, if we just added the syntax for locally abstract parameterized types, that would be another route to sort of a similar goal. What are your thoughts about that?
I think adding a new syntax type for parameterized type might be a bit complicated, because afterward we need to do unification on higher order types. With parameterized type doing unification, it's easier when you have inference, constraint-based inference. So in a way, I don't think it's that easy to do it in the OCaml compiler as it is. However, one thing that we most likely will need in the future is to be able to restrict signatures to a parameterized type, such as when having a function that take two modules as argument, and we want to say that both modules define the same parameterized type. This is something we cannot do currently. But having a type A with a parameterized type, I think this might be a bit complicated. But hopefully someone will find a way, I hope.
Okay, thanks.
Thanks for the talk. So in OCaml, you also have applicative functors that creates a new kinds of module paths, so-called application path. Do you also support application path in modular explicits?
Yeah, with modular explicit, which is just a way when doing application to be able to do the types correctly, as it's not doing currently with a first-class module. However, we support all the features of typing outside with types that currently exist, which is the case for applicative functors.
Awesome, thanks.
Any further questions? Actually, I have a quick. Do you want to go now? I have a quick question. Have you thought about what should happen with subtyping coercions if you feed a dependent module or module-dependent function in?
Yeah, so for answering this question, we thought about it. The main thing is that when doing subtyping, we want to do subtyping without doing any code generation. So to do this, we need to not change too much the type of a function, and we want to have a function that have the same runtime value. So to do this, we need that the two modules that are given as argument needs to have the same runtime representation, which means that you cannot reorder values inside the signature, but you can reorder the position of types, and also you can remove a few types that are unneeded from the signature, or add, depending on how you see the subtyping.
Cool, thank you. Did you have a... yeah.
So this introduces dependency between function arguments. So that sort of implies that function arguments need to go in a certain order. How does that interact with labeled arguments that maybe you sort of partially apply a function with labeled arguments such that then we need to eta expand and sort of get things out of order? Does that pose a problem?
Currently how labeled arguments work is that when doing the typing, we reorder the arguments in the good order. And so if you have a module-dependent function, it will try to look for the module that is given as argument. And if this module is given, you can just type the function with this argument and continue typing the rest of the function afterward. But this creates a barrier that we type directly this argument compared to other labeled argument currently where you type the arguments after distributing and unpacking the type of a function. And when the type of the module is not given, and we cannot remove the dependency. In this case, we just fail saying, okay, you cannot remove the dependency.
Okay, thanks.
Okay, let's thank the speaker again.